Okay, so unlike most other previous presentations that I make during class where I talk about that as a prelude to learning module, and according to your syllabus, this should be a prelude to learning module 6. But my expectation is that I shall not have a learning module 6 for you. I shall provide between now and 9 p.m. tonight whatever you need for the learning module. I will have a couple of videos for you to watch, specifically in terms of using regression, using R for regression and R commander for regression. I shall provide some videos on that. I shall also provide some more information on using statistical assumptions for regression analysis. Okay, that we can discuss in our next week of class as we start looking into writing statistical reports. Okay, so but today what I'm going to teach you is how you typically write a business report for everyday business purposes that you can share with colleagues at the workplace, uh, frame a discussion about what those numbers mean, and take it from there. A more detailed statistical report writing will be discussed in the next week of class. And I shall provide a couple of videos between now and next class that will help you understand how to set up assumptions for the regression analysis, and also how to do it in R. But what I am going to discuss between now and the end of the session today is basically a 7-step approach to um, statistical decision making using regression analysis. And we will use the uh, the housing price example in our discussions. And more importantly, um, this is how I will teach this part of the class and going forward the rest of it, because I have provided you all the nuts and bolts. Um, in many cases, I will do the work for you, but in some cases, I will hold your hand partially. Okay, so I will tell you what needs to be done, but it would be your job to complete that task. Okay, so as you will see in this discussion tonight, I will give you an overview of what regression analysis ought to be, what are the steps required, how to think through that. But I wouldn't do the exact entire work for you. Okay, so there will be something for you to be done by yourself. Okay, and so make sure that you take notes of that. Of course, right after this class is over, once I have um, the recording, I should upload those recordings for you to review. And based off of that, you will complete um, this housing data set analysis on your own, and that would be part of your assignment. I'll talk about the assignment as well before the class is over. So what Dr. B has here is a uh, 7-step process, okay? A 7-step approach to um, doing linear regression. And we'll look into each one of these steps. Some of the earlier steps that we'll discuss, we have discussed at the beginning of this semester. So I won't spend a tremendous amount of time on this. So step 1 is finding a simple problem statement for the problem at hand. And that essentially helps you identify your Y variable. So if I look at my data set, so this is my data set. As I can see, there are a bunch of homes here. Um, in essence, there are 128 homes. Okay. And I have data on which neighborhood they're coming from, how many offers are there on the plate, the square footage, whether it's a brick house versus it's a non-brick house, number of bedrooms, number of bathrooms, and price. Okay, so that's basically the data. If you recall the discussions that we started off about formulating the problem, the question that we are asking is at the step 1, what is a simple problem statement? Okay, the simple problem statement actually helps you identify your Y variable. Okay, so understanding home prices, that's essentially what you're after. Okay, so price is your Y variable, the response variable, the one that you're after. Okay, that's the problem at hand. That concludes your step 1. Your step 1 is unique, and it's small and short. Understanding that home price. In step 2, you extend the problem statement by identifying the x variables. So your x variables are all of the others. So neighborhood, offers, square footage, bedroom, bathroom, brick, right? And so from a conceptual standpoint, can we make a bigger bucket of these variables? So as an example, if I bucket these variables together, square footage, bedroom, bathroom, and brick, can I give a name to this group of variables? And this is not a statistical question. It is just a,
Those are like characteristics of the house itself.
yep. And then maybe broadly, can I say that neighborhood and offers have to do with what?
Like desirability?
Okay, and I remember that I think you used the same exact term last time too, Sarah. Very good. So desirability and home characteristics, broadly, how they are impacting the price of the home is where your extended problem statement is. And that actually also allowed you to identify your X variables. Everybody with me? Yes, no? Next step, draw the conceptual model. We have already talked about this form and direction of association. Again, we discussed this in much more detail when we talked about correlation and scatter plots and so on and so forth. But very broadly, if I look into price as my y variable, okay, I have neighborhood. Let's think of this as an x1. I have offers. Let's think about this as an x2. I have square footage. Let's think this is x3. I have bedroom. Let's imagine this is x4. I have bathroom. Let's imagine this is x5. And then what am I missing? Brick. Okay, so form and direction. First is direction, right? So your direction is, they're all directed towards the y. Okay, so y is a function in this case of x1, x2, all the way till x6, right? That is what you are writing. And plus, you are still using what we define as an error term. So in other words, you are saying that very broadly, for at a 30,000-foot view, you are describing the conceptual model as your price being y, being impacted by all of these factors for which you can actually account for because you have data for those factors, and everything else that you cannot account for is your error that you have not captured in this model. So in the same way we discussed in the context of ANOVA, you want this error to be low. Okay, you want these factors to together explain the variability in y, so much so that you can define this model as a valid model. That's what we are after. Only when you can define this model as a valid model can you look into the regression coefficients and see where each one of these factors impact the y or not. Okay, so that's where the idea of direction comes in. So all of these are directed towards y, they impact y. That direction arrow mark is critical, because if you don't put an arrow mark, you does not provide your reader an understanding of who is y and who is x. The x's point towards the y because they are impacting y. Your y is a function of those x's. And now we look at the form of it, okay? And so we'll start with um, the ones that are much more easier first, and we have done this before. Typically, the more number of bathrooms, your prices are expected to increase. So if your bathrooms go high up, your price will also go up. So that's a positive relationship. Bedrooms, the same story. Square footage, the same story. What about offers? And I'm asking, I'm playing the devil's advocate here. I just don't know which way to go with offers. So let me hear from some of you, and whichever way you go, I'll go with that. As to where do you think offers impact price, or do they impact price?
More offers generally increase the price because you have a
Okay,
bit more.
okay. So I'm going with Lawrence setup of more the number of offers, the price also increases. Okay. Um, a brick house typically is more pricier than a non-brick house, so I can go with that assumption, if you will. And then neighborhood, and this is a dicey one because I really don't know which direction I want to go with this one. So right now I'm keeping that as a plus versus negative because I don't know which neighborhood um, is really impacting it. I can always do the visualization of the data. I can break the data down into the three neighborhoods and do the um, box plots and all of that jazz, and get a feel of which neighborhood kind of turns out to be more than the other. You guys already did that exercise for me at the beginning of this semester. So when we looked into those box plots, we looked at it that neighborhood 3 turns out to be having a much higher pricing range than the other neighborhoods. And but again, it's very sample specific, right? So you can't really infer from there. The inference has to happen from something like regression analysis. Okay, so that's where the conceptual model piece of the puzzle ends. Now, the next important step is um, identifying the data types and understand if there is a need for coding of data or not. Okay, and so I'll go back to the previous step, and I shall actually identify the data types right here, and I'll keep it very simple. I'm going to use two terms. N is for numerical, C is for categorical data. Okay, so N is numerical data and C is categorical data. So what I want to do here is real quick, number of offers. This is numerical data. Square footage is numerical. Beds numerical. Bathrooms numerical. Brick is categorical, and neighborhood is categorical. Okay, so um, that is what I am capturing in the context of identification of data types. Now, is there a need for coding? Again, for Excel to draw a regression analysis in Excel is only around numerical variables. And so absolutely, in the context of offers, square footage, bedrooms, bathrooms, we have no problem. Okay, that's already numerical data. And price is also numerical data. So we are good on the y-axis or the y variable side. The problem is with the brick versus no brick and the three neighborhoods 1, 2, and 3. So if you think about this as a factor, as we looked at, this is a factor in terms of house characteristics with two levels, brick and non-brick. Here is a factor of neighborhood with three levels or three treatments, neighborhood 1, neighborhood 2, and neighborhood 3. Neighborhood as a variable has a pseudo feeling of being numeric, but in reality, it is categorical data. And the moment you come across something like categorical data, tell yourself, I have to do something about it to convert it into a numeric data. Okay? And that's where there is the need for coding. There is an absolute need for coding. So this is where I also want to introduce a few Excel etiquettes here. Okay? So the first one is, and this is something not just for me or for this class, but anytime you mess with data, this is something that you should always keep in mind because it will make your life easier. Um, what I'm going to do here is, if you look at the tab on the bottom, it's called data. I'm going to click on that tab, right click on that tab, and first rename that. I'm going to rename that as raw data. And this tab is renamed as raw data primarily to remind me, the analyst, that I don't want to mess with this data set. I can mess with it somewhere else in Excel, but there should be at least one point in the Excel file where my data set integrity is kept. The original data is kept the way it is. It is very, very important because so much gets lost in translation as you keep working with the data set. So first and foremost, rename the original data as raw data, and then you right click on that tab, choose move or copy, select create a copy, and then move it to the end in that same file and hit OK. And so it now creates a copy of raw data. As you can see, it says raw data with a parenthesis 2. I want to rename that as coded data because this is where I'll be doing the coding. Something else I want to do so that it helps me later on in my future steps is I want to bring the categorical variables on one end and I want to bring the numerical variables on the other end. It'll actually help me. And I still want to keep my y variable on the farthest end because it's a good opportunity for me to eventually work with Excel functions later on if I have the y variable on one end. It can be the left end or the right end, doesn't matter. Now what I want to do is, you see the square footage and brick. The brick is a categorical variable. So what I want to do is I choose that brick variable, the entire variable. So I take my um, mouse on that column E and I click on that column. That entire column is selected. I right click. Okay. I cut it. And here after neighborhood, I want to insert those cut cells. Okay. So when I say insert cut cells, it now moves my brick column right next to neighborhood. And all of this is being done in coded data. I am not messing with the raw data. Okay. The other thing that I have to do is, because neighborhoods and brick, these two variables are categorical data, I have to recode them. So I'll clear all of these content that I have on these cells. Okay, so I'll choose all of these cells and just hit the delete button. That way I have no content anymore under neighborhood and brick. And this is where I'll do my coding. So far, so good. Yes, no?
Yes.
So let's go back to our PowerPoint.
Dr. B, a quick question. Would you still leave the labels on the top, or do you have to, because you're removing the data numbers, are you still leaving the labels on the
Your
top?
labels still remain the same. If I have to change the labels, I'll do that later. Okay, there may be certain situations in which the label needs to be changed. We'll talk about that. Okay, so let me talk about a very simple coding form that each one of you have come across in some form or the other. So when you look at a gender of MF, typically, okay, MFFM, this kind of a data, okay, have you ever seen that gender to be coded as 1001, that kind of a data? Has anybody ever seen that kind of coding before?
Yes.
Right? So this is in binaries. It's basically taking 0 and 1. Okay? So this kind of coding scheme, by using these variables, they are called dummy variables. Okay, so the dummy variable concept is very simple. The first question you want to ask yourself as a coder is, how many columns of variables will I have in my code? Okay, so the first question you ask is, how many columns? Okay, and the answer is one less than number of levels. So we just talked about levels in a factor, right? So if this is the variable or factor gender, how many levels does the gender have in this data set? The levels can also be defined as treatments. How many levels does the gender factor have? That's a question for you guys.
2.
2. And so if there are 2 levels in that factor, how many columns of coded variables will I have?
0 and 1.
How many columns?
1.
1 less than the number of levels. There are 2 levels, and so the number of columns is 1, and that is that single column of information. That's where the 0 and 1 concept comes. The 0 and 1 concept now depends on who you want to fix as a reference and who you want to move. Whichever you want to use as reference will be your 0. So in this case, we are using the females as 0 because we are using the females as a reference point. And then, of course, we are defining the males as 1. But we can apply all of them together in the same context, in the same column. So the same thing can be said of this data set. So brick versus no brick. Okay, so the way you have the data, the original data has your bricks as being no versus yes. So if it is a brick house, then it's a yes. If it's a no brick house, then it's a no, right? So when you go to the no versus yes, and imagine that this is how your data set is set up. Let's say we are defining this house as a brick house using non-brick as a reference. Okay, so if it is no, then it is 0. If it is yes, it is 1. If it is yes, it is 1, and so on and so forth. Again, this had 2 levels. You convert them all into a single column of data, of numeric data in terms of zeros and ones. So this is something very simple. Each one of us have used that in the context of gender mostly. And anytime it's dichotomous, where it is only one versus the other, it's much more simple. So what I want to establish is, how do you define this in the data set? So in the data set, the way, if you recall the data, you have the data as yes, no. Okay. You want to convert that into a 1 0. What do you do in Excel? Question for you. You have the data set as yes, no. You want to convert that column into a 1 0. What do you do in Excel?
Would you do an if function?
Very good. You want to do an if function. Okay, so let's talk briefly about the if function. The if function in Excel has three parts to it. Okay, when you type the if function, so when you type equals if and then you press the first parenthesis, Excel starts talking to you, and it essentially gives you these three options. The first option is your condition. So for a certain condition, you are testing. If that condition is true, then whatever that true value is, you will put in else. The second comma basically is corresponding to the else function. Else, it will be a false value. So in this example, you would probably write something like if that specific data cell is yes, and again I put yes in quote unquote because it's a character, then what should my new cell value be? If the old cell value was yes, what should the new cell value be?
1.
1. And if it is not yes, then the value should be
0.
0. So that in its basic simplicity is how you design your if statement. Okay, so let's look into that design process in Excel. So we go back to Excel. So we are going to make that design in our coded data sheet, right? So this first house brick value is where I would code the data, right? And so I type equals, I type if, and then it actually describes the if function for you. It says checks whether a condition is met and returns one value if true and another value if false. And then I put in the first parenthesis, and as you can see, there are three parts to it. That's how Excel starts talking to you in the same way you did the norms inverse, norms dist, where Excel started talking to you, right? The same thing happens here. It starts talking to you and it's asking you what's the logical test against which you are trying to generate values. And so this is where I can do a cellular reference. So my logical test can very well be by looking into the other tab. So I can basically click on that raw data tab, okay, and choose that first cell from the break column for the first home, which is that specific cell. So the way it reads is it's saying if from the raw data tab E2 cell, and that's how it's reading, right? And I have to give some definition, right? So what is that cell about? So if that cell equals, and I'll type yes, I want to make sure that I type it in the same character, in the same way it is provided in the data set. So an uppercase Y for yes. And so if raw data tabs E2 cell has a value of yes, and if these were numeric values, I wouldn't have to put quotes, unquotes. The quote unquote is put only because these are characters and I'm converting that character into a numerics, right? So when I put the comma after this, then it's asking me in the coded data set, what value would you give if that logical test is true? And so in the raw data, if E2 is yes, in the coded data, that corresponding value would be 1, right? And then I put a comma again, and I only have two outcomes here, right? I only have a yes versus a no. And so this is much easier. I just press 0. So that's essentially saying that if the raw data tab E2 cell has a value of yes, it should give me a coded value of 1. Else, it'll give me a coded value of 0. So right now, what is the value of E2 cell in the raw data?
No.
What do you see? The raw data E2 cell. What is the value there?
No.
No, right? And so what should the coded value be?
0.
0. So when I hit enter after I complete the parenthesis, right? On the coded data set, that value turns out to be 0. And it is pulling that information from the raw data set, from the raw data tab, right? So that is basically how that value is generated. And guess what? I click on all of those. I right click on the lowermost, on the lower right corner of that tab. I double click on that, and all of these are generated accordingly. So you can see 0, 1, 0, 1, all of those values are generated based off of whether the original data value was a yes versus whether it was a no. So that's how the brick column has been coded.
Dr. B,
Yep.
could you do that once more um, to multiply that for all the other values?
Yeah. So all you do is once it is done on the one set, right? On the one cell, once it is done, all you do is take your cursor to the bottom right corner of that cell when it becomes a more pronounced plus sign, and then you just double click and it'll generate all the others. You could also drag. There are multiple ways to do it. But yes, don't try computing this for each and every cell. That defeats the purpose. You'll keep cursing me for the rest of this week.
So what happens if I did that and I got zeros for all of them?
Then in my humble opinion, you made a mistake in your function. Maybe
Sure.
you did
Oh,
not put the quote unquote for the yes.
Yes, I see the mistake. Thank you.
So that was relatively easy. Now here is the real fun piece of the puzzle. And I want to go back to the setup first because the setup is important. It's a simple question we ask. How many columns? Okay. It is 1 less than the number of levels. Okay. So suppose I have education data for a certain class, a foundation studies class that I'm teaching. And a student at any level can take that class. And I'm looking at grades. Okay. And I'm looking at the student level. And that level is graded as a freshman, a sophomore, a junior, and a senior. And I want to convert this into a set of dummy variables. So my first question is, how many columns do I need for my dummy variables against this level?
3.
3, absolutely 3, because there are 4 levels. Okay, so this is the level of education. I don't want to confuse. There are 4 levels in this factor. Okay, the factor is level of education. There are 4 levels in that factor. And therefore, the number of columns that you will use is 1 less than the number of levels. So in the male-female case, we used the female as a reference, which is why we used the male as 1. In the brick, non-brick case, we used the non-brick as a reference, and therefore we used brick as a column, and we used the value of 1 for brick. Let us suppose here we are using only the 3 columns showcasing sophomores, juniors, and seniors. In other words, I'm using freshmen as a reference. So here is how it will pan out, and this is where it becomes quite interesting. Let us suppose the raw data is this way. So I have 1, 2, 3, 4, let's say I have 100 students, okay? And so I have the grades of those students here, and I have the student level. Let's say the first level is a sophomore, the second student is a junior, the third student is a senior, the fourth student is a senior, the fifth student is a freshman. Okay, so this is how my raw data is set up. And my job is to convert this raw data into what I call coded data. Coded data meaning that I am recoding some of these factors that have multiple levels into dummy variables. And as we just discussed, because this specific factor has 4 different levels to it, I can actually set up my dummy variable by choosing 3 columns only, that is 1 less than the number of levels. So when I redo my coding for this first row of data, the first data set comes from a student who is a sophomore. Okay, so under the sophomore column, is this coming from a sophomore? Yes, no. The question you ask is this a sophomore? Yes, no. It's a sophomore. So the sophomore is given a value of 1. Is it a junior? No. Is this a senior? No. And that is what the coding happens for that first row of data. In the second row of data, that belongs to somebody who is a junior. So when you record that, is that data point a sophomore? No. Is the data point a junior? Yes. Is the data point a senior? No. The third one is a senior. So when you record that, is it a sophomore? No. Is it a junior? No. Is it a senior? Yes. Ditto for the fourth one. The fourth guy is also a senior. Is it a sophomore? No. Is it a junior? No. Is it a senior? 1. The fifth one is a freshman. How do you record that?
0, 0, 0.
0, 0, 0. Basically saying not sophomore, not junior, not senior. And that is the beauty of dummy variables, where using 1 less column, you can still represent 4 different levels of a factor. The fourth one, essentially the one that you are using as a reference point, would be all zeros. So under that same context, if I have neighborhood, which is 1, 2, 3, whatever those values are, 3, 2, 1, whatever that neighborhood is for each of those data points or each of those rows of houses. If I have to make a conversion here, how many dummy variables, columns do I need for the neighborhood variable? Nick Davis says 2. Everybody agrees? I have 3 levels here, 1, 2, and 3. And therefore, I shall have 2 columns of dummy variables. Now, the question therefore is, okay, Dr. B, which 2 should I choose? That depends on you. It doesn't really make a big difference, no difference actually, in the overall outcome. Okay, I would go ahead and choose neighborhood 2 and neighborhood 3 as my 2 columns. In other words, I am using neighborhood 1 as my reference. So let us imagine if my first data point is neighborhood 1, how would I code that? In the first row here,
0,
if 0 and this guy,
0.
0 and 0. If my second one is neighborhood 2, how would I record that? This is neighborhood 2, and this is, of course, neighborhood 3. It's not neighborhood 3, so it's 1, 0. Okay, the third one, if it's neighborhood 3, I would record that as 0, 1. Not neighborhood 2, yes, neighborhood 3. Okay, and so on and so forth. So that is how I would completely record this entire data set in terms of neighborhoods 2 and 3. So far, so good. Yes, no? So here is your first assignment. I want to insert another variable here. I want to call it neighborhood 2, and I want to rename this as neighborhood 3. So your job is to do an exactly similar task that we did with brick, using if statements to redesign those codes for neighborhoods 2 and 3. Okay, you cannot hard code these. You have to use the if statement to do that. So that's the first piece of the puzzle for you. Okay. Now, once your coding is done, now you have the data set that will allow you to build the overall model equation. Okay, so in essence, what you have done is this is your revised functionality. Your price is a function of neighborhood 2, neighborhood 3. What else do we have? Brick, square footage, bedroom, bathroom, offer, plus whatever that has not been captured in the data set. So plus an error term. Okay, so that is how you would want to represent. And this is a very, very 30,000 foot view of the overall problem setting. Your price, you're trying to establish the pricing of the house as a function of all of these variables, along with whatever you could not capture in your data set. Right? So to be a little bit more statistical with this, anybody remembers what the equation of a straight line is? The slope intercept form, anybody remembers? We have talked about this multiple times before. Ashley?
Y equals mx plus b.
Mx plus b, right? Where m is the slope and b is the intercept, right? So we will apply that same format, only with some changes in um, the alphabets that we use in the context of regression. Okay, so a very base case equation, this is when the data has not been analyzed, is where you are saying y equals, and I'm going to rewrite mx plus b as b plus mx, which is where you are, so that you can see the commonality. In this case, you have only one x. In this case, I have multiple x's, right? So let's suppose this is x1, this is x2, and I'm going to change the color so that it's easier for you to comprehend. So this is x1, this is x2, brick is x3, square footage is x4, bed is x5, bath is x6, offer is x7. Let's suppose we have all of these 7 variables. So the way we write this is this is beta, the Greek letter beta with a subscript of 0 or beta naught or beta 0. That is equivalent to your overall intercept. Okay, so beta naught plus beta 1 times x1, where your x1 is neighborhood 2 and your beta 1 is the slope of that variable, plus beta 2 times x2 plus beta 3 times x3 plus all the way to beta 7 times x7 plus an error term. So this equation represents the entirety of how price of a home is impacted. This does not represent just this data. This also represents the error term, which basically means what if we are missing out on some variables that will impact the price. If those variables are taken into consideration, then we will also see that error. Whatever you are not being able to take into consideration is your error term. Okay, so that is where this model equation is essentially designed before even you frame your regression. As you run your regression, now you are building your analysis off of this sample only. So now you are looking at an expected value of y. So that hat that you see on top gives you an expected value. So that then becomes this hat plus beta 1 hat times x1 plus beta 2 hat times x2 all the way till beta 7 hat times x7. There is no more error term here because this is much direct. This is what is coming out of your data. When you analyze the data, this is the equation that you are trying to solve. You're trying to find the values of all of these coefficients. You're trying to figure out to the extent to which the intercept is there, the extent to which x1 impacts y, x2 impacts y, and so on and so forth. You're trying to find those values. There is no more error term here. That is why those hats represent the expected value that is very specific to this sample of 126 home listings. A different sample would have given you different data points. So the first equation gives you a generic. It's a generic equation of everything possible. The second equation is more specific. This is specific to the data set that we are dealing with. This does not include, as you can see, that error term. That error term ensures that we are taking into consideration everything possible under planet Earth.
So Dr.
So,
B,
yep.
is our model equation, are we writing out the generic and the specific?
We will write it in two different parts. The generic is written when you design the conceptual model.
Sure.
The specific one is written when you actually do the regression.
Okay.
Before you do that, we check for what we call confounding. Before we run the regression, we check for what we define as confounding. Okay, and we have talked about confounding in the past. Okay, so in other words, I have x1 that impacts y. I have x2 that also impacts y. However, if there is a very high correlation between x1 and x2, then what happens is that one is influencing the impact of the other over y. So one is curbing down the influence of the other over y because of the very high correlation between them. So that is not always an expectation. And this is where this phenomenon is called multicollinearity. You don't want multicollinearity in the model. But what I most love about this approach is this allows you to look at the problem not as an analyst, not as a numbers person, but also as somebody who is trying to understand what those variables mean. Okay. So the question therefore is, Dr. B, multiple questions. One is, what happens if there is a high correlation between the X variables? What do you do? So the typical norm is that you take one of those variables out. Okay, you take one of those variables out. And then your question would be, which one do I take out? Also, the other question is, what is high? When you say a high correlation, what is a high value of correlation? So this is where all the discussions we had on correlation comes back to help us. If you recall, between two variables, the correlation coefficient was R and the corresponding explainability was R square if you frame a straight line. So if your R is zero point 0.6, your R square is 36% in terms of explainability. So is there a magic number that you should seek? The magic number that's typically used in the academic world is an R value of 0.71. As long as your R is less than 0.71, you can say that the correlation between the two variables are low enough. What happens is when your R becomes 0.71 or more, then your R square value becomes more than or equal to 50%. In other words, you are saying that there is a more than or equal to 50% explainability between the two X variables. That is enough for us to make a judgment call that one of them is confounding the effect of the other, and one of them has to go. But again, I implore you to wear the business hat, because chances are, as you deal with this data set, I'm just giving an example. Imagine that this X1 is bedroom and X2 is bathroom. Okay. Typically, when you have bigger houses, higher the number of bedrooms, your bathroom size will also increase, right? And so you may find a high correlation between bedrooms and bathrooms. And so as you draw the correlation, you can satisfy all of these mathematical gibberish, but will you really take out a bedroom or a bathroom from your model? And the answer is no. And this is why I ask you to always wear your business hat as you make that decision as to whether you want to keep a certain variable in the model or take it out. Okay, this is a quick cross check more than anything else. And the way this is done is it creates something that we define as a correlation matrix. So a correlation matrix in this case would be something like Y, X1, X2, and you have Y, X1, X2. And so these correlation values are all one, right? I am correlated to myself at 100%. Okay, so Y to Y is 1, X1 to X1 is 1, X2 to X2 is 1. Now, the fun part begins here. When you talk about the correlation between Y and each of these X's, okay, let's say this value is 0.7, this value is 0.8. Okay. My first question to you is, between the Y variable and the X variable, if you are trying to design a model, you want the correlation to be high or low? Between the Y variable and the X variable?
High.
High, right? You always want that very correlation to be very high. But that is not what causes confounding. When you are looking for confounding, you are not looking at these values. All you're looking at is this culprit here, the correlation between X1 and X2. And it's the same value that you see here. It's the mirror image. Okay. Imagine that correlation is 0.9. So suddenly you see that it's a very, very high correlation. And I'm not talking bedrooms, bathrooms here. I'm just giving a generic example. that correlation is 0.9. So definitely there is a high chance of confounding, and then one of x1 or x2 has to go. And then the question you would ask yourself is, so Dr. B, which one do I take out? Do I just wake up in the morning and tell myself today x1 is my favorite or x2 is my favorite, or there is some logic behind it that is showing off right away in this table that allows me to make the logical decision that one of those variables x1 or x2 has to go. If that correlation turns out to be 0.9 between x1 and x2, so the correlation that we are after is between the x variables only. And if that correlation is 0.9, I know for a fact that one of those variables have to go. Which one will I take out and why? In this example?
The one that has the lowest correlation to y.
Very good answer. So the one that has the lowest correlation to y would be a logical step in terms of finding the variable that needs to go. Now here in this case, you have 0.7 and 0.8. They are very close together. It's very hard to differentiate between the two. If I were the analyst, I would keep both x1 and x2 in the model and let the regression take care of that cleanup process. However, if this one was 0.3 and this one was 0.8, that's a very clear identification that even though x1 and x2 internally are very highly correlated, that gives me an idea that they're confounding against each other. When you compare their values against y, x2 is clearly much highly impacting y compared to x1. So I will take out x1 from the regression model and run my regression. But it again depends on how that correlation turns out to be. So in our example, if you go back to the data set, what I would create is just a new sheet, and I'll rename that sheet, let's say as correlation. Okay. And all I'll do here is go to data, under data analysis, there is a tool called correlation. Okay, and this correlation basically measures the correlation matrix. Now, one of the assumptions of running a correlation, if you recall the discussions of correlations in the beginning of the semester, is that all the variables have to be numeric data, not categorical data. You can't run correlation in between categorical data. You can use categorical data to split the data set, visualize that for each category. But correlation has to be run around numeric data only. So if you recall, in the coded data section, I made you put the numeric variable on one end and the categorical data on the other end. There is a reason for that, because it will allow you to run your correlation in a more smoother fashion. So now I hit OK, and it asks you what my input range is. Okay. And so I click on that input, I go to my coded data, and I choose everything from offers till price. Okay. And I keep on choosing that. And so all of this has been chosen. It's grouped by columns. There are labels in the first row. And of course, my output range is right here on B2 in this correlation tab. Okay. So as you can see, I'm in the correlation tab, which is where I want to place my output, but the input range was chosen from the coded data tab, and I hit OK, and it basically provides me a correlation matrix, if you will. Okay. So again, when I'm looking at confounding, I am really not looking at these data points. That's the least of my concern, because these data points that I have put in green are basically giving you the correlation between each of the other numerical variables and price. That's not where confounding can happen. Confounding happens only when you are looking into correlation between the X variables. My X variables are offer, square foot, bedroom, and bathroom, numerical variables. So thankfully, I have tested this out. None of them are over 0.71, so I can put all of them in my regression model and I can run my regression. So this is just a pre-check to understand how your data is behaving. It's pretty important that you run this because it gives you a good feel of what to see in your regression. Now, so before we actually run our regression, let's talk about interpreting a regression equation to infer, because there are two parts to the process here. Okay, and I'll explain to you both these. One is, let me go back to some basics. Y equals 3x. How do you interpret that in the context of relationship between x and y? Simple answer. Somebody? Sarah Al-Zarani. Y equals 3 times x. How do you interpret this in terms of relationship between x and y?
So you could say that x is like 3 times smaller than y, right? Because
so y is 3 times x and x is 1/3 of y. That comes straight from the equation. My question is, in terms of relationship, when we talk relationship or association, we are talking about the rate at which they move. Okay, so if x increases, what happens to y and so on? That's the question I'm asking.
if x increases by 3 or more, I don't know. Well, I don't know how to phrase it.
Okay, so what happens to the equation if x takes a value of 1? What is y?
3.
If x equals 2, y is 6. So how do I frame that in a sentence? That for every unit increase in x, y increases by
3.
3 units. Does everybody get that? That's the simplest form of stating an equation. For every single unit, for every unit increase in x, y increases by 3 units. What would I say if y equals negative 3x?
For every unit increase in x, y decreases by 3 units.
Very good. For every unit increase in x, y decreases by 3 units. So if I said price equals 100 times bedroom, let's say this is how my final equation turns out to be, and I'm just looking into one of those variables. How do I interpret that? How do I infer? What's the relationship between bedrooms and price? Let's put another 0 to it. Same idea, guys. Same thing that we just talked about. We are just giving meaning to the variables y and x here.
Or
Go ahead, Sarah Shikora.
okay, for every unit of bedroom that it increases, price increases by 1,000 units.
So now we don't have to use the term unit anymore because we know exactly what the unit is,
Yes.
right? So we say that for every extra bedroom, price increases by $1,000, right? That's the way you infer or interpret the situation. The same thing can be says as, let's say price equals 100 times square foot. How would you interpret that, Leslie? Leslie, you there? Okay. Isabel, price equals, oops, sorry. Price equals 100 times square foot. How would you frame the relationship between square footage and price? Turn on your microphone. Yep.
Would you phrase it as like square foot is 100 times like
Same idea as we did here. Okay, if price equals 1,000 times bedroom, what would we say? We say that for every extra bedroom, your price increases by $1,000.
Oh,
so
okay,
if price
so
equals 100 times square foot, what do you say?
price would increase 100 times when you would add square feet.
So for every square footage, your price increases by how much?
By 100 times?
Times or some other unit? What is the unit of price?
Dollars, $100.
Okay, so for every square footage, your price increases by $100, right?
Yes.
So that's how you would want to interpret an equation, because that is important. I can, and this is where I go back to trying to understand the problem process first, because I can teach you how to take a regression output, but you'll have no way of interpreting that if you don't get these basics right. Okay, so what is common between these examples that we looked at? Y equals 3x, y equals negative 3x, price equals 1,000 times bedroom, price equals 100 times square foot. So what is common between all of these is that both my y variable and the x variable are numeric. Both my y variable and x variable are numeric. So it is a very easy, this comes straight from your high school understanding of basic straight line, right? Y equals 3x basically means if x increases by 1 unit, y increases by 3 units. You put that same context into all of these relationships. So that part is pretty cut and dried. The fun begins when in my equation, I come up with price equals 10,000 times brick. Because here I have made a difference in the sense that brick is my not traditional numeric variable. I have used a dummy variable to run the regression in Excel so that Excel can read that and run it. But brick is an essentially categorical variable. It's a brick versus non-brick. If you recall, the way we designed the dummy variables was setting up non-brick as my reference. So brick was 1 and non-brick was 0. So my question to you is, when you infer about this relationship, that inference is not the same as the previous ones we discussed. You can't say if it's a brick house, the price increases by $10,000. Well, it's the right statement, but it has to say more than that. What is it actually saying? When it comes to the two variables both being numeric, it's a very straightforward approach. If one increases, the other also increases. When you are dealing with data, or especially variables in this case, where the variable is categorical, you are always comparing to the reference point. And so the best way to infer or interpret this relationship is to say that brick houses cost $10,000 more than, can somebody help me complete my sentence?
Non-brick houses.
Non-brick houses, because your non-brick was your reference. The reference of 0 is what you are comparing it against. So your brick houses cost $10,000 more than your non-brick houses. So if we go back to how we framed our neighborhoods, if you recall, we said that neighborhoods have 3 levels, 1, 2, and 3, right? And therefore, when we set up our dummy variables, we are setting up one column less than the total number of levels. So let's say we set neighborhood 2 and neighborhood 3 as my 2 columns, using neighborhood 1 as my reference. Okay. And so then we have all of these equations. And finally, it turns out that price equals, let's say, 14,000. And don't ask me where I get these numbers. Okay. I'm just putting in whatever comes to my mind right now. This has no significance. These numbers are coming from Dr. V's thought process. Okay. They don't have any source. So price equals 14,000 times neighborhood 3, let's say. How would you interpret this relationship? Somebody I have not heard from yet. Ryan, how would you interpret this relationship?
Would it be neighborhood 3 houses is 14,000 more than neighborhood 2 and 1?
Hold on a second. You are on the right track. You first have to ask yourself, so neighborhood 3 comes from a stack of variables of which there are 3 levels, right? Neighborhoods 1, 2, and 3, right? And of which my reference point was neighborhood 1, right? Because I have chosen neighborhood 2 and neighborhood 3 as my 2 columns. I'm using neighborhood 1 as my reference. So I gave you that hint. You're on the right track. You're saying neighborhood 3 houses cost 14 grand or $14,000 more than homes in
neighborhood 1.
Neighborhood 1. So that reference point allows you to make the inference in that format. So in that same way, if I said that price equals 8,000 times neighborhood 2, you would say that homes in neighborhood 2 cost $8,000 more than homes in neighborhood 1. Always that reference point, the one that you have not considered in your column, is what you are comparing against. Always, always, always. So far, so good? Interpretation is critical. This is the most important piece of the puzzle for a business person. I can run on the analysis, but if I can't interpret, then it goes down the docks. So the next piece of the puzzle, and before I run the regression, and you'll actually run the regression, I'll show you how to run it, nothing more. I want to explain to you the typical parts of a regression output, because this is critical and this will help you as you make the analysis. So in essence, there are 3 parts of a regression output. Okay. The first part is what I define as explainability. Okay. The second part, and I'll come to the second part later. Let's go by each part. So in explainability, all you are doing is you are saying how powerful your model is. This is where you are looking into your R-square value for the entire model. If you recall, when we talked about R-square defines the extent to which the combined model, model meaning all of your x factors, explain the change in y. And so you want that r square value to be high, right? So if you look back at the way we set up this equation, you want all of your models together to properly explain y. You want that error term to be as low as possible. If that error term is very high, your model is useless. So your R square is coming from the combined impact of all of these taken together. To what extent are all of these variables capable of impacting a change in y? And therefore you want your R square value to be very high. And that is what the first part of the regression output will show to you. The second part of the regression output, and this is why we studied what we did in the first session tonight, is a basic ANOVA table. And so this is essentially asking the question, is the model valid? Is it a good enough model to work with? And so you have every right to tell me, doctor, didn't we just talk about this in the first part, the R square? Doesn't the R square also tell the same story? And you are spot on. They are complementary. They tell you the same story. So the ANOVA with your p-value, if your p-value is less than alpha, you are essentially saying that, yes, the model actually makes an impact. And anytime you are able to say that, guess what your R value, R square value is supposed to be? A good high value. Ideally, your R square value should be more than 80%. But you will see certain cases in which it is not necessarily that scenario. But if you have a high explainability, guess what happens here? Every time you'll be able to reject the null hypothesis. And you'll be able to say that your p-value is less than alpha. And so your model is valid. If your R square is 20%, okay, guess what will happen here in the second case? Your p-value will be more than alpha. Your model is no more valid. And that's the only time you should be happy for this class, because then you don't even have to worry about the third piece of the puzzle. You stop right there and say, Dr. B, I don't have the right data set. There's nothing more I can do about this. This model is useless. I can't proceed. However, if your R square is a healthy number, which basically means that you have a good level of explainability, if your ANOVA table gives you a p-value that is less than alpha, which basically tells you that your model is valid, that's when you look into what your regression coefficients are. And so this is where you will see all of your coefficients highlighted, starting with the intercept, and then you'll have neighborhood 2, neighborhood 3, break, square footage, bedroom, bathroom, offer. So all of them will be highlighted here. And then you'll have coefficients of all of these variables. And so these are your beta naught hat, beta 1 hat, beta 2 hat, beta 3 hat, and so on and so forth. Okay, so this is what we were talking about in this specific equation, where your expected value of y is your coefficient of the intercept plus coefficient of your x1 plus coefficient of your x2 plus coefficient of your x3 and so on. This is specific to your data because now you have analyzed your data. But then that is not where it ends, because if you see all those coefficients, you will have a natural tendency to say that, oh, you know, my final equation is that entire equation. But this is where regression tells you whether each of these variables are statistically significant to stay in the model or not. And that is where you will see a t-test and a p-value for each one of these variables. And The expectation is exactly the same. If your p-value is less than alpha, then that specific variable stays in the model. If your p-value is greater than alpha, that variable cannot stay in the model. So your final equation will only include the variables that stay in the model based off of the p-value for each of those variables. And I'll explain this with the example. But that is how you want to interpret a regression equation. So what you want to do is, when you go back into your week 2 data set, and so in your coded data, right, um, once you are able to code the neighborhood 2 and 3 in, you would run this entire data set and you would run the regression. And so I would create a separate tab here, okay? And I would call that, rename that tab as regression analysis. Okay, so all I do is I go under data, under data analysis, and if you scroll down, you'll see the option called regression. I choose that option, hit OK, and it's asking for the Y range and the X range. Okay, I'll start with the Y range. I check that, go into my coded data. My Y range is essentially this price, right? Because price is my Y variable. So I choose the price column, including the price label. Okay, and so that becomes my Y range. My X range would be, in my coded data, all of these others except the first column. The first column, don't make that mistake of choosing the first column. The first column is just a count. It doesn't really help me with anything. But I'll be choosing all of these together. Of course, you have to populate neighborhood 2 and neighborhood 3 first. But each one of these are my X variables. Neighborhood 2, 3, brick, offered, square foot, bedroom, bathroom. Including the labels. I'll choose them all. And therefore, I shall check the fact that labels have been chosen. I'm going to use a 95% confidence level. And I'm going to use an output range, let's say in this new regression analysis tab at the cell B2. Okay. And I shall not check anything else. I'll discuss these later on in a video that I shall share with you. We'll discuss this in the next class. Residuals, testing for assumptions, normal probability plots, all of that jazz. Don't worry about anything else. You will just hit OK. If I hit OK now, it'll give me an error because I have no data for neighborhood 1 and 2. But that is what you are supposed to do. And all of this is recorded in this video. So you can review this as you do the work. But as you do that, what you will see here is an output that is very similar to this output. Okay, so there are these are the three parts. Oops. So this is the first part that basically provides you the explainability, that gives you your R-square value. And as you see here, and this is where I'm talking about the Excel etiquettes as well, I have also mentioned very clearly what that R-square value means in the context of the problem by using a comment box. What does the second part of the puzzle say? So this is your explainability. It tells you that together all of those X variables explain 86% of the variation in price, which is a very high explainability. It right away tells you that it's a good model to work with. When you run the ANOVA, and now hopefully all of these values make sense. I had 128 homes, and therefore total degrees of freedom is 127. this is the overall variability in the data set, of which 79639, all of this huge value is attributed to the regression or the model itself. The residual is what my error is. And so that is only a very small piece of the puzzle. My F value is very high and the corresponding P value is 0.0000. It's very small. P value less than alpha? Hell yes. And because it's less than alpha, now I can start looking at my regression stats. So everything that you see here is in the context of your coefficient, and that actually helps you tell the story. But before I tell the story, I ask myself, what does the p-value suggest? And the p-value essentially tells you that, well, the intercept, and there are multiple lines of thought on this. There are some professors who will tell you that, don't worry about the intercept. The intercept has to stay because it's part of the model. But you want to look into all the other p-values that correspond to the x variables. And as you can see, except for the neighborhood 2 piece, everything else is significant. They're all very small values. They're all less than alpha, which basically means all of these, they stay in the model. Neighborhood 2, that variable does not stay in the model. So now that we have talked about the inference part or interpreting part, let me ask this question. Let me start with the easy one. Bathroom. The bathroom has a coefficient of 7883. Okay, so in other words, your home price equals 7883 times bathroom. Isabel, you and I were talking about this example. Let's go back to reality now. How do you want to interpret this in the context of the problem? When I say home price equals 7883 times bathroom, what does it mean in the context of the problem? How do you interpret that? Turn on your microphone.
You would interpret it as
the same thing that we talked about in the previous slide with the other example. So for every extra bathroom, your price will increase by
$100.
Well, that was the example that I said. In this case, what would the answer be? For every extra bathroom, your price will increase by?
Is it 7,883?
Yes, it is. Don't question
Oh.
yourself. You're right. Okay, so for every extra bathroom, your home price will increase by $7,883. Timothy, how do I explain bedrooms?
For every extra bedroom, the price would increase by $4,246.
Fantastic. What about brick? And I should ask somebody that I have not talked to yet. Let me see. Nathan.
So it looks like if the house is brick, then it's going to sell for 17,000 more than if it is not brick.
Fantastic. So in other words, a brick house costs 17 grand more than a non-brick house. Okay. Now, how about square footage? For every square foot, what happens in the way I want to infer? Ping. Square footage. Ping, did you turn on your audio? Ping, can you hear me?
Oh, sorry. Sorry, right now I can. Can you hear me
So
right now?
how do you explain the square footage part?
increase 1 square foot, the house price will increase 52.99.
So for every square footage, your home price increases by 63 bucks, 52 bucks, sorry.
Yeah.
Where is Lauren? I want to come back to Lauren for a different reason. Lauren, do you recall that when we set the hypothesis, we said that if the number of offers increase, the price of the home also increases, right?
Right.
Right. So what happens here? It
Well, it
turns out
looks,
that for every offer, the home price reduces by 8 grand.
yep.
And the point I made when we first talked about decision making in the business world and how lucky and blessed we are compared to general sciences, where you would eat your brains up if you can't frame the hypothesis properly, is there is always a story to say. Okay, so this is where we need to start thinking on those grounds and ask ourselves, what in terms of dynamics is happening here? What could be the reason that as there are more offers on the table, your price is gradually decreasing? What's going on here? Can we explain that dynamic? David.
You ask your question again, please?
So my question is, as you recall, when we first set this up, Lauren talked about a hypothesis, which is the normal hypothesis to make, that okay, if my offers go up, I would think that okay, then this price is on hot sale, so the price will also go up. But it turns out that based off of this data set, as my offers go up, my price is going down. So what may be happening here? And there is no right answer here, guys. I'm just asking you to think from a non-statistical standpoint, just to put yourself in the shoes of how houses sell and what happens. Maybe the home is already overpriced, which is why it is not selling and the offers are coming in, and it has to reduce prices every time to bring in more offers and stuff like that. I don't know what that right answer is. That is up to you to come up with. But think through that. Neighborhood 3. Hunter.
So that's saying that the houses in neighborhood 3 sell for $20,000 more than the houses in neighborhood 1.
Very good. So neighborhood 1 is your reference point here.
Yeah.
Now, the question that you may ask me is, well, Dr. B, you have set this up as neighborhood 2 and neighborhood 3, and this is how you did your coding. Could we have coded this as neighborhood 1 and neighborhood 2 and use neighborhood 3 as a reference? The answer is absolutely yes. That would change these numbers here, but the impact would be exactly the same. The impact wouldn't change one bit. But in this case, because we coded this as 2 and 3, our reference is 1, and so we are always comparing between neighborhoods 3 and neighborhood 1. Final question. What do you make of neighborhood 2? Ashley.
That potentially maybe that area just has lower value houses, or maybe not even the best.
Say that again. I couldn't hear you properly.
That neighborhood might, since it has a negative value in reference to neighborhood 1, that maybe it has a lower value
than neighborhood 1. And so what Ashley is saying is, because it has a negative 1560, neighborhood 2 houses sell at 1560 less than neighborhood 1 houses, right? Is that what you're saying, Ashley? And that would be a correct interpretation, except something happened in the p-value here. The p-value was 0.5162. It was a very high p-value. So it basically tells you that yes, you can't even keep neighborhood 2 in your model. And more importantly, statistically, there is no difference between homes in neighborhood 2 and homes in neighborhood 1. And therefore that value of 1560 is very small. Right away you see that those numbers are extremely small. But if that p-value was low or lower than alpha, if that was a small p-value, we could have kept neighborhood 2 in our model, and we could have inferred that homes in neighborhood 2 cost $1,560 less than homes in neighborhood 1. But the fact that your p-value is greater than alpha, you are essentially saying that there is no difference between the homes in neighborhood 2 and homes in neighborhood 1. Statistically, there is no difference. Does that make sense? So that is how we complete our inference. And therefore, when you write your final equation, that equation should also include only the variables that stay in the model. Okay, so as you could see, home price is, it includes the neighborhood, offers, square foot, break, bedroom, and bathroom. I didn't include intercept because from a p-value perspective, that value was also very high. But there are multiple lines of thought here. Many people think about using the intercept anyway. So you could go either way. But neighborhood 2 does not stay in that final model. And hopefully now you understand how you want to infer from each one of those relationships, because they all tell a story. And hopefully you understand how that inference pattern is different when you are comparing numerical data. So, price to offer, price to, square foot, price to um, bedroom, price to bathroom. That's a very standard straight line equation that we have learned all along through high school. If the x increases by 1 unit, the y increases by the coefficient value. Okay, so if bathrooms increase, one extra bathroom means price increases by 7,800. One extra bedroom means price increases by 4,200. One extra square footage means price by 53. But when you are looking into the variables that are dummy variables, you have to take into consideration the reference point. So neighborhood 3, essentially that coefficient tells you how much or how low price is. That depends on the plus versus negative sign. In this case, it's a plus sign. So it tells you that neighborhood 3 homes are 20 grand more pricey than neighborhood 1 homes. What made me say neighborhood 1? Because when I designed my dummy variables, I designed it using 2 and 3, using neighborhood 1 as my reference. Okay. In the same way, when I did brick, I did brick 1, and so non-brick was 0. So non-brick was my reference, and it's essentially telling me that brick houses cost 17 grand more than non-brick houses. Okay, so that is the fundamental difference in which we want to infer. So your job is twofold. Your job is to first complete the coding in the way we have discussed in class. And once that coding is complete, you run the regression in the way we have just discussed. And again, I'll have this video available for you in the next few minutes so that you can review that process. And once you have that regression, this is what I want from you. And this is the standard protocol of simple business reporting. I'm not looking into very hi-fi statistical reporting. We'll talk about that in the next class. I want you to create a tab called summary. Okay, and I'm going to move this summary tab all the way to the left. Okay, this is where your Excel file has to start behaving like a website. Okay, so your summary tab is your standalone tab. This is where you will define, provide an overview of the problem. Okay, so make sure that you are able to wrap the cells. Okay, so sorry. So this is where you provide a summary of the problem. Um, in the next wrapping sector, you may provide something like key recommendations. And here is the fun part. I do not want to see any statistical jargon here. This summary tab is being read by people who don't understand statistics. You see how I have set up the output on the regression tab with all of these um, comments, equation, all that jazz. That can all stay in the regression analysis tab. In the summary tab, it should be simple, short, concise, to the point. Here is the summary of the problem. Here is what I was after. Here are my key recommendations. Okay. And what you would want to do is create something like navigate to correlation analysis. I'm giving an example here. Navigate to regression analysis. So what helps here is, and I'm giving you one example, you can pick on this and do the others. So navigate to regression analysis. What I'll do is I'll first choose these cells together. Okay. I'll right click. I'll go to the format cells. I'll go to alignment. I'll wrap the text. I'll merge the cells. I'll make this central and I'll hit OK. And so this is a single cell now, and I can, of course, provide a color coding to it. I can give borders to it. Okay. But once I have provided this border, what I should be able to do is I right click on this entire cell. Okay. And if you're using a newer version of Excel, you will see an option called link. In the older versions of Excel, that option is called hyperlink. Okay. So you click on link and it will give you multiple options. By default, it's asking you provide the HTML address, something from the internet that I can link to. But I am providing a link that is being placed inside of this document. So instead of existing file or web page, I'll choose place in this document. And because I am trying to navigate to the regression analysis, guess what? I'll just choose that regression analysis tab here. That is where I'm placing in the document. I hit OK. And so now a link has been created right here in the summary. As I read my summary, I click on this link. I am transported to my regression analysis tab. And of course, you are already thinking that how do I return back to summary? I want to create a return to summary or something like that that will help me come back to my summary tab from the regression tab. And so if I hit return here, it takes me back to my summary tab. When you eventually save your file, you should save your file while it is in the summary tab. That way, when I open up your file, I open it up as the summary tab. So that is one part of your homework. Okay, so we have done most of this work already in the class. Just a few loose ends. Do the recoding, run the regression. Your numbers should match the numbers that you see as an output in my presentation. And then start creating this summary. Make sure it is simple, concise, to the point, no statistical jargons. Okay, there is no p-value, alpha, and all that jazz. All of that can happen in all of those other tabs. This is where you are reporting to a layman, somebody who doesn't care about stats. Just give me the answer. Give me what I need to know out of this problem. What is important to me. Okay, and make it as attractive as you can, because I want to also enjoy reading your work. So clean up the workspace, use the view tool, clean up the grid lines, make it look clear or clean everything that I have talked about, Excel etiquettes, this is your opportunity. So this is one part of the assignment. The other part of the assignment, if you recall, as a team, you had to work on a data set on operations risk of countries. Okay, so you had all of these country level operations risk and heritage foundation index, transparency, and all that jazz. So that data set is back to you. Okay, and this time there is a very specific question that will help you apply regression analysis on that data set and everything else that we have learned. So if you look under your assignments, there is an assignment called assignment 6A and 6B. There are two Excel files attached to it. The first one is of course this file, but I would appreciate the fact that you are already working alongside me today, so you're already a little bit through. But again, this video will be available to you. And then the other Excel file is the other operations risk file, and it has a specific question posed there. Fulfill the instructions properly, um, and put Excel etiquettes into consideration, but that should be the last piece of the puzzle. First, you have to run it and make sure that the process runs. Okay, the meat of the matter should be there. And then you have to ornament that process. Ornamentation is essentially explaining what it means. That's where some of the comment sections come in the context of your regression analysis, writing the output as a as a as an equation, creating the conceptual model. And so you can do all of those things as part of Excel. Okay, so um, within Excel, you can do um, you can insert shapes, you can do all kinds of things to create those shapes for the conceptual model and so on. Nick Davis, you raised your hand. Question.
Oh, yes. So will assignment 6B still be an individual assignment, correct?
Assignment 6A and 6B is strictly an individual assignment.
Thank you.
Okay. No collusion, no collaboration. Collusion is a wrong word. Sorry. I don't want to make it political, but no collaboration, please. The only collaboration that you are allowed is with Dr. B. Okay. So if you have a question, try me. I'll be more than happy. But there are two problems. You should start with this one because this is almost done. You already know what needs to be done. You finish this and you apply the same approach to the other problem. The only way to learn this process and to comprehend it is to practice more. Therefore, I've given you two problems. Okay, but understand that there are two separate Excel files. So when you submit your assignment in, I'm going to say this again, when you submit your assignment in Blackboard, make sure that you attach both the files before you hit the submit button. I don't want one file submitted to me via email and 20 emails in my mailbox saying, Dr. B, I forgot the other one. I won't take it this time. Okay, do it right the first time. Quality at the source. Questions? So if you have, if let me quickly stop the recording.